it says projectile motion with linear drag. But I'm thinking about this, and it might not actually be projectile motion, because a projectile motion, I think, is defined as the motion of an object just due to the influence of gravity. So just have them empty force on. Okay, but let's just get started. So I want to find the equation of motion in both the x and y direction for an object that's moving under the presence of two forces, the downward gravitational force, and then a drag force in the opposite direction as the velocity. And so I'm using this is why it's linear drag. It says that the drag force is some constant times the velocity. So whatever way the velocity is going, the drag force is in the opposite direction. And in this case, we're going to use, it's not super important right now, but this b parameter should depend on two things. It should depend on the size of the object. If it's a sphere, let's say it's a tiny sphere, d is the diameter, and beta is a property of the shape and the material. So if it's like air and a sphere, okay, then you know beta. I've already done linear drag in one dimension without gravity, so now we're going to do it in two dimensions with gravity. And I'm going to repeat the first part in the x motion will be essentially the same as what I did before, so I'm going to go through that a little bit faster. If you want to see the video on that in more detail, my playlist link is down below, and you can go look at that. Okay, so I have these two forces acting on an object, and I want to find its equation of motion. So, of course, the first thing we need to do is to start with this. Newton's second law, F net is ma. And both of those are vectors. And then, so this is just going to be Fd plus mg. And it's plus mg because, yes, g is usually in the negative y direction. It won't be in this case. Haha, it's going to be a fun joke. But those are contained in the vector part of it. We don't put negative. And the same thing's true for this. It could be in any direction, really. So if you look up here, let me redraw I guess I can draw it up here. Let's call this the x-axis. And I'm going to call this downward the positive y-axis. So in that case, this drag force, let me get a marker, colored marker, has a component in the x and the y direction. And since v is a vector, and this is a vector, and they're just multiplied by a scalar, then I can say the following. F dx is negative b vx. F dy is negative b vy. Right? They have to have equal, the components have to match up. So this is kind of a big deal. So now if I have the x component here, I can just deal with that in the x acceleration. So I actually get two equations here. I get max equals f dx. There's no x component in the gravitational force. And then may is f dy plus mg. Okay, so again, g is 9.8 newtons per kilogram on the surface of the Earth, and it's plus because, I had down as positive. And that just turns out to be an easy trick. You don't have to do it that way. So these two equations become and then ax is just going to be dvx dt. It's the derivative of the x velocity with respect to time, and for f dx, it's going to be negative b vx. So that's a differential equation that only depends on vx, and that's kind of cool. And in fact, this is exactly the problem I solved in the past video, but I'm going to do it again. And then in the y direction, I have m dvy dt. Right, that's the y acceleration, and this is going to be negative b vy plus mg. So now I have two differential equations that don't depend on each other. This one only has vx in it, and this one only has vy in it. So I can solve those two independently. Okay, let's just jump right to it, and let's solve this one. Although, like I said, this is the third time I solved that one before. Okay, so here's my equation, m dvx dt, and I'm going to be very careful about the vx. I know that we could just drop that, but I'm not going to do it. Negative b vx. I'm going to divide both sides by m, and I get dvx dt equals negative b over m vx. And then I can separate these variables because I can get all the v's on one side and all the t's on one side. dvx vx is negative b over m dt. Now I can integrate both sides of this equation. Like I said, I'm doing this fast. And then in indefinite integral, I'll add a constant. And if I do that, I get the integral of dv over v is going to be the natural log of v, ln of vx. And this is going to be negative bm, is just a constant, b over m, and then t. And then plus a constant. And then at t equals 0, vx is equal to vx0. So let's put in t is equal to 0 and put vx as vx0. So that gives me ln of vx0 equals negative 0, right? That's all 0, plus c. So c is going to be ln of vx. Now, I'm just going to skip a step right here. If I subtract that from both sides, I get a difference of natural logs, which I can write as a ratio. So I get ln of vx over vxo is negative bt over m. Now I want to get vx as a function, so I'm going to take the inverse natural log, which is the exponential of both sides, and I get vx over v0 is e to the negative bt over m, and then I can multiply both sides by v0 and get vx as a function of t is v0 e to the negative bt over m, and that gets a box because it's important. That's an important equation. So I actually, this is vx0, x0. I told you I was going to be careful, and I wasn't. Okay, so that's an important equation. That's the same equation I got before in one-dimension motion, but now it's just the x. So then I can write this as a derivative with respect to position. So I can write dx dt equals vxo e to the negative bt over m. I can get the variables separated again. There's no x's over here, so it's pretty easy. Multiply both sides by dt, and I get dx equals vxo e to the negative bt over m dt. Now I can integrate both sides. Vx, this side, indefinite integral. So this is going to be just x. And then over here, I'm going to get the integral of the exponential is the exponential because the derivative is the same. But I have to take care of this term here because if I went backwards and I took the derivative, I'd get a negative b over m. So I have to add that, include that negative m over b. So I get negative m over b vx0 e to the negative bt over m plus c. And again, x0 at t equals 0. So if I put that in, I get x0 equals, if I put in 0 for t right here, this just becomes 1. E to the 0 is 1. So I get negative m vx0 over b plus c. So now if I solve this for c, I get c equals x0 plus m vx0 over b. So now I can put my x equation, x as a function of t, it's going to be equal to this stuff, xo plus, I'm actually going to get this plus this term, I'm going to factor this out, so I get m vxo over b times 1 minus e to the negative t bt over m. Box it. And again, that's what I did before. I did it before and it took me 30 minutes. I did it in 9 minutes this time because I skipped some steps. But there you go. So now I have the velocity as a function of time and the position of function of time for the x motion. That's kind of important. Now let's look at the y equation. So here I have m dvy dt equals negative b vy plus mg. Now that's going to be more difficult to get the variables to separate, so we're going to use a trick. Okay, I've already used one trick, so here's my trick counter. Trick 1, 2. I've got 2 tricks so far. One was calling positive y down, which doesn't really make sense at this point. But here's my other one. So let's write the velocity in terms of the terminal velocity. So let's choose terminal velocity. Why am I writing it out? Okay, so just when you write that out, it makes me feel like I'm taking forever. I'm going to call that VT for terminal velocity. So at terminal velocity in the y direction, we have a ball, we have the gravitational force pulling down, and this is just the y direction, and then the drag force up. And when those two forces are equal, then this will move at a constant velocity. So it won't keep speeding up forever, because eventually, as it gets faster and faster, this term is going to be equal to that term. And so at that case, that's terminal velocity. So when these two forces are equal, we have terminal velocity. So I'm going to say BVT equals mg. And so I could solve for terminal velocity, but I'm not going to. Instead, I'm going to put it in up here. So I'm going to rewrite this as m dvy dt equals negative bvy plus bvt. And I can write that, I can factor out the b, I can factor out the negative b. So I can say negative b, because then it looks like the same thing. Vy minus vt. Yep. So you see, maybe you can see, one of the things about solving equations like this, you can either know the trick or you can have solved so many of these that you see the trick. But here I see a term, Vy minus Vt, and I see a derivative, and they can be, I could do a u substitution where these two things would be the same. So let's call it u. Let's say new variable u equals Vy minus Vt. And if I do that, that becomes u, and then I can say, let's take the derivative of u with respect to t, and that's going to be the derivative of Vy with respect to t, which is Vy dt, minus the derivative of the terminal velocity with respect to time, but the terminal velocity is constant, so minus 0. So dvy dt is du dt. So over here, I can rewrite this as m du dt equals negative b u. That's kind of important, because now we're in the exact same situation we were before, right? I could say du dt equals negative b over mu. This is the same equation I had for the x. It looks like the same as a one-dimensional equation. For u, not v. You, me, us, all of us. Okay. So again, I'm going to separate the variables. I get du u equals negative b over m dt. If I integrate both sides, I get the natural log of u equals negative b over m t. Now, plus c. Now I can say at t equals 0, u is going to be what? Well, at time t equals 0, vy is v0, right? So u0 is going to be equal to vy0 minus vt. It's just, you can see it right up here. That's constant. So I do have a different u0. So if I put that in, I get natural log of u0 equals negative b over m times 0, that's 0, plus c. So c equals ln of u0, which is not v0. That is different. And then I can substitute that in the same as before, and I get u equals u0 e to the negative b t over m. Now we can substitute in our u and our u0. Okay, so let's do that. Okay, so I'm going to start with this. U equals vy minus vt. u0 equals vy0 minus vt. And then u equals u0 e to the negative bt over m. Okay, so let's just substitute the stuff in. For u, I'm going to put this. For u0, I'm going to put that. So I get vy minus vt equals vy0 parentheses minus vt times e to the negative bt over m. Okay, can we substitute a little bit? Let's just solve this for vy. Vy, I'm going to add that to both sides, is vt. I'm going to multiply this out because I think it's going to help me. Plus vt e to the, no, it's going to be minus vt e to the negative bt over m. And then I'm going to get this plus vy0 e to the negative bt over m. So over here, it's not super needed. Let me see how I did this before. I can't remember. Hold on, let me check. I'm looking at my notes. I actually do have notes. I did take notes. Looking, what did I do? Yeah, I wrote it that way, but I shouldn't. I should keep it in terms of this, right? I'm going to write it like this. So Vy equals Vt plus Vy0 minus Vt e to the negative bt over m. That way I only have one term with a t in it. It just makes it, I think that's going to make it a little bit easier. Okay. So again, that's actually important. That's my velocity as a function of time in the y direction. I'm going to put a box around it. Okay, so now we can do the same trick. I can say, I can define v in terms of y. So I'm going to say dy dt equals vt plus vy0 minus vt e to the negative bt over m. And then I can multiply both sides by dt, and I get dy equals vt plus vy0 minus vt e to the negative bt over m, and all of that times dt. Now I can integrate both sides. Okay, so this is not too terrible to integrate. The integral of dy is y. And then over here, I have a vt dt, so that's going to be vtt. And then right here, I have this term, and then I have an exponential. So I'm going to have to do that same trick. I'm going to have to multiply by the derivative of the 1 over the derivative here. So I'm going to get negative m over b vy0 minus vt e to the negative bt over m plus c. Okay, then y equals y0 at t equals 0. So if I do that, if I plug that in, I get y0 equals vt times 0, which is 0. And then this term is just going to be 1, so I get minus m over b vy0 minus vt plus c. So c is going to be equal to y0 plus m over b vy0 minus vt. And if I put that all together, y as a function of time is going to be vt, I should put that, that's fine, vtt minus m over b vy0 minus vt e to the negative bt over m plus y0 plus m over b vy0 minus vt. That, okay, so I have that term right there and there. Yeah, I think combine those two together. So let's write this as y as a function of t equals, so I have this y0 term, I like to put that first. y0 plus vtt plus, these two terms together is going to be plus m over b vy0 minus vt times 1 minus e to the negative bt over m. Yeah, I like that. So, let's look. I never interpreted these two equations, and so we should do that. Up here, as time gets really large, what happens? Well, this term goes to, as t gets really large, this term becomes small. And so this whole thing goes to 0. Okay, so at large time, the final velocity is just going to be v2, vt. That is what you would expect, right? It starts off at t equals 0, then you get the initial velocity is vy. That does work, right? Because that's 1, and so you get minus vt plus vt. So that's pretty good. Also has the right units. Down here, what's going to happen? Well, as time gets really big, this term is going to go to 0, so you just get 1. So you just get this term, which is just a constant. And that term is a constant. And the only thing that changed with time is vt. So this agrees. This says it's moving with a constant velocity as y approaches infinity. So I think that's right. Okay. So now we're going to make a graph. And just like before, I'm going to do it 2 ways. Okay. So I'm going to do a numerical calculation of the motion of a ball. It's a tiny bead of water. Okay, I'm going to use a drop of water, 2.2 millimeters in diameter with initial speed of 1.5 meters per second. And so I can calculate B and all that stuff, which I don't really care about. But I am going to calculate it. So in my numerical method, I'm going to do the following. So I'm going to have my drop of water. It's going to have some velocity v at some instant. And the key to this is to break the motion into tiny time steps. So if I have the gravitational force mg going down and then a backwards drag force. So if I calculate F net is Fd plus mg, that's going to be equal to ma. So from this, I can calculate A. A is equal to Fd over m plus g. Now, if delta t small, then I can assume this acceleration is constant, which it's totally not constant. But let's just say it is. So let's say delta t is 0.001 seconds. That's a pretty short time. And if that's true, then I can write the acceleration as delta v over delta t instead of a derivative, a finite difference. And so this is going to be, if I think of the velocity at the beginning of the time interval as v1 and at the end is v2, this is v2 minus v1 over delta t. If I solve this for v2, I get v2 equals v1 plus a delta t. That's important. That's important. So now I can find the velocity at the end of the time interval, and then what I can do is use that to find the velocity at the beginning of that, as the beginning of the velocity at the velocity at the beginning of the next time interval, and I can recalculate the acceleration because it depends on the velocity. And then I can redo this, and I can calculate all the velocities in order, v1, v2, v3, and so forth, using this method. What about the position? Well, I can again assume that the velocity is constant, v2 equals the change in position, delta r over delta t. So that's going to be r2 minus r1 over delta t. And so if I solve that, I get, for r2, I get r2 equals r1 plus v2 delta t. So here I'm using v2 because I just calculated the velocity. So I'm going to assume that the velocity is constant. I know it's not because I just changed it, but that's fine. And use that to find the new position. And then I'll update time. T2 equals T1 plus delta T. That's important. And then go back up here and repeat the whole thing. So I'm going to calculate the acceleration, update the velocity, update the position, update time, and then just keep doing that all over again. So we're going to do that in Python. And then after that, I'm going to plot the trajectory. And once I plot the trajectory, I'm going to plot another trajectory using my equations of motion that I solved for using the same parameters. Does that sound fun? Okay, it's going to be fun. So let's switch over here to Python. So I've already entered some stuff into Python here because it's just not important. Make that super big. So there you go. Let's move this over a little bit. Okay. So this is GlowScript v Python. It's a embedded Python-like environment. in a web page. So I already have the diameter, I have the density of the water, I have beta for air in a sphere. I calculate the mass of the drop. That's important. It's just the volume times the density. It's the volume of the sphere. I calculate B, I calculate G, and then I pick the initial velocity and the angle. So let's make one more thing. I'm going to do this with vectors, so I'm going to actually need another value for G. I'm going to need a vector value for G. I'm going to call it GV equals vector 0, negative G 0. So now I can treat that as a vector. That's important. Next, I need a vector velocity to start with and a vector position. So let's call this VV for vector velocity. And it's going to be equal to V0, the initial velocity magnitude, times the vector cosine theta, 30-degree angle, sine theta, 0. Now I need the initial position, so I'm going to say R equals vector 0, 0, 0. So we're all set. Okay. So now what I need to do is to make a loop. Oh, I need this. Time equals 0, dt equals 0.001. dt instead of delta t, because I don't want to type out delta, because that's just silly. Oh, I do need a graph. So up here, let's make a graph. G1 equals graph, title, linear, drag, x title, title. It's just x. I'm just going to make a trajectory. And then the y title is y. I'm flying over the graphing part because I don't really care. Width equals 500. Height equals 250. If you don't do that, the graph ends up usually being pretty big, and I don't like it. So let's say F1 equals G curve. Color equals color.blue. And this will be my numerical calculation. I can put a label in there. I'm not going to. So for the loop, I'm going to say while r.y is greater than or equal to 0, right? Because I want to shoot it from the ground until it gets back down to the ground. So it's going to start at 0, and I have to include 0 as a possible answer. Otherwise, it would say, oh, it's 0, I'm done. So I have to have greater than or equal to 0. The first thing I'm going to do is calculate the net force. F net is going to be M times G. And in this case, I know it seems stupid, but I actually do have gravity y is up. I don't know why I did that, but it's too late now. Okay, so it's mg minus b times v. V is the vector, right? So that's the net force. From that, I can calculate the acceleration. I'm not going to. I'm just going to use F net. And I can update the velocity. So VV equals VV plus F net times dt divided by m. F net over m is the mass, is acceleration. And this is, I point this out every single time. And I don't get tired of it. It's no big deal. V equals V is a update value, right? It's not an algebraic equation. So those VVs don't cancel. And that way we don't have to do all the indices 1, 2, 3, 4, and so forth. Okay, now we need to update the position. R equals R plus VV times dt. That's easy. Now we need to, I'm going to plot it, then update time. So F1.plot, the trajectory, I can't plot a vector, but I can plot the x and y components. So I can plot R.x, R.y, and now I'm going to update time. T equals T plus dt. I think this is going to run the first time without any errors. But let's see. I'm open to errors too. See, I got an error. Cannot subtract a scalar and a vector. I know what I did wrong. G, V, ha. I knew it right when I did it. I forgot. That was my fault. But mistakes are fine, right? Okay, so I'm pretty happy because it looks like what you would think. And more importantly, it's not a parabola, right? Because this side is steeper than that side, which is what you would have happen. Once it gets up, it slows down, so its x velocity is not going to be as great. So you do get this kind of thing. So that's my numerical calculation. It looks fine. Now I'm looking over here at my equations. I can plot the y and I can plot the velocity and the position, but I only really need the position. So let's just do the position, just to save time. So I need down here. Okay, so I have the initial velocity but I need the initial x and the initial y velocity because I need those as variables. I'm looking at my equations here. I need mb vxo. I don't have vxo. I have t. That's the only thing I need. Vxo. I need the terminal velocity too. Okay, so let's see. Let's write down the terminal velocity here. Vt is going to be equal to m times g. That's it, right? Divided by b. Okay, so I have that. That's in my equation. I need Vx0 is going to be equal to V0 times cosine theta. Vy0 is going to be equal to negative V0 times sine theta. It's negative because, remember, my solution, the way I wrote it, down is positive. So if I shoot it up at an angle, then that would be a negative velocity, and that seems weird, but that's what I have. I think that's it. I need another graph. So let's go up here. F2 equals G curve. Color equals color dot red. And then down here, I need to calculate x. I need to calculate y. And I can do that. I haven't used x and y variables. So I'm going to type in my x equation. X equal, I need x0 and y0. x0 equals 0. y0 equals 0. So x equals x0 plus m times vx0 divided by b. This is m divided by b. I'm going to just do that. M divided by b times 1 minus the exponential of negative bt over m. Aha! B times t. Caught it. Okay, that's x. And then y is going to be equal to, looking at my equation right here, y0 plus vt times t plus m over b times vy0 minus vt times 1 minus e to the negative b times t over m. I just don't think this is right. Okay, it could be right. Sometimes you're right. Okay, oh, I didn't mean to do that. That's fine. Let's plot that f2 dot plot x, y. If this works, I'm going to give myself a double high five. Just letting you know. I'm pre-warning you that if this works, double high five. Okay, run. Oh, ha! It almost worked. I know I did wrong. So remember that I actually need to plot over here negative y because my numerical calculation had up y. This one has down y. I'm just going to give myself one high five because I'm pretty sure that was good. I'll put the negative sign there and run it. And now here comes my second high five. Good job. Okay. Now, I actually like this a lot because they're not exactly on top of each other. There's a slight difference. This is just a tenth of a second. And so if I broke this into 0.001, this is just 100 loops for the numerical calculation. So let's go over here and make that 1,000 loops. So I'm going to make dt even smaller. And now they're right on top of each other. Okay, so that's good. I'm pretty happy with that. Did I save the code? No, I didn't. Should I save the code? Yes, I should. Linear drag in 2D. Save. And you are going to get that code. Okay, so down below, I'm going to put a link to this code and a link to my classical mechanics playlist. This is where I'm putting all my new videos for the new semester of classical mechanics. You can find the linear drag in 1 dimension video down there in that playlist if you want to go back over that first thing that went through pretty fast. So, okay, that was fun. I can't stop. There it is.